This week's seminar is being presented by yours truly. That would be me, John Soule, and I'll bring those slides up in a minute. Let's go ahead and get that going right now, actually. I want everybody to get a piece of paper, just a sheet of regular old paper out so that everybody can have that available here because we're going to use it. So here is our, here's my background. So I've been sailing since I was probably around 8 years old or so, and found a boat that wouldn't work and had to rebuild it to make it so it would even float. I just got involved in lots of stuff with little boats, and in my mid-teens, I designed and built 2 boats. Both of them can best be described as an utter disaster. And so in the case of the first boat was a sailboat. I had modified the plans in what I thought was a reasonable thing to do. It turned out to be a really bad idea. And those modified plans resulted in a very tippy boat that was, in fact, so tippy, it was somewhat comparable to standing on a floating log and trying to stay upright. So it was, by any measure, not a particularly successful boat hull. My second attempt at building a boat was a power boat. And there are some times when I think back about my childhood, and it's actually fairly surprising I survived. And that boat kind of worked overtime to kill me. It was not successful, but it wasn't for lack of trying. And so that hull was also a disaster, or at least the fact that I had a motor on it that was probably about 5 times the size as that hull could handle didn't help either. So anyway, I decided at that point in time to give up boat building, and haven't built a boat since, but I've kind of got out of sailing for about 30 years, except an occasional trip here or there, and then got back into it a few years ago when Sherry and I bought this boat right here, the SS Scholarship. And then you can attribute the name to Sherry. So that's the boat that we now have. And so there we have it. So I guess a little bit more on my background. For a short time, I was living aboard a merchant vessel as a diesel mechanic. It wasn't a very big boat. It was 203 feet long, which for a merchant machine as a work boat, it was not all that big. And I was spending my time rebuilding and maintaining large diesel engines, and decided that wasn't a very good way to make a living, and instead decided to go finish my physics degree. Since then, most of the boats I've been associated with have been in the 8-foot to 20-foot range, and so all pretty small. Some of the people who are here are way more skilled sailors than I am, and also have boats substantially larger than boats I've spent any kind of substantial time on. And so I'm glad that those people are here, and hopefully they'll find something of interest, if nothing else amusing, in today's seminar. One of the things about sailboats is that you can't really be a sailboat owner and not be concentrating on speed to some extent. You're always trying to get your boat to go a little bit faster. Whenever 2 sailboats are even in vaguely the same direction, it doesn't matter if one of them is a 60-foot long racing sloop and one of them is a 15-foot long dinghy. There's a race on, and the skipper of the dinghy is going to be absolutely convinced that she's not going to be beat easily. And so everybody's trying to go as quickly as they can. Usually we kind of like not really want to launch our sailboats, but the idea here is to get some speed. That's what we're going to talk about today, is how do you make a boat go? What limits the speed of a sailboat? So to get there, what I want to do is I'm going to start with a review of how sailboats work on a very basic level, how the motor works, in other words, the sails, and then we're going to look at the limiting feature, which is the hull. We're going to go ahead and work our way through this and see what we can do about figuring out what limits the speed of a sailboat. And big inside tip, it's going to be the hull that limits our boat's speed. So basic sailboat. Pretty much all modern sailboats are some version of this. There are boats that are bigger boats that have multiple masts and stuff like that. But the vast majority of sailboats are going to have a single mast with a mainsail off of that, pronounced a mainsail. It's going to have a sail in the front called a headsail or a jib. And you'll see variants where you might see, instead of just one jib there, there'll be two, but for the most part, it's the same basic idea. So this is your basic boat, and each of these parts has a function. So looking at these parts, what we see is that the mainsail and the headsail are your motors. That's what makes the boat go forward. But the other question is why, when you blow the wind sideways, does the boat go forward? Well, the trick to that is the keel. And so the keel does two things. It keeps the boat from keeling over, and it keeps the boat from sliding too much. All boats will slide a little bit. The other features that you have in here that are pretty critical is you got to have a rudder. If you don't have a rudder, you're not going to be able to steer it. But that also provides some sliding resistance as well. The obvious point to the hull there is that it is nice to do this and stay dry in the end. So taking a look at your really basic sailboat. So I've gotten rid of the second sail here and moved the mast forward a touch just to be able to make something fairly simple. And so here is your really basic sailboat. This would be like a small dinghy with a sail on it. And so you've got the wind coming in here from the left and it's blowing sideways and your boat goes that way. How does that work? Well, you got forces on here, of course. And so you have multiple forces on the sail and you've got forces on the control surfaces below the water, the rudder down here and the keel. So those forces, if we label them, we'll see that there are two forces on the sail. We have a dynamic pressure here, which is just basically the wind blowing on the sail like a just like a parachute. And then the aerodynamic lift is how a sail works with wind flowing over it, much like an airplane wing. And so you have an airflow that goes around the back of the sail, providing lift, just like an airplane. And you get a low pressure by Bernoulli's principle on the one side, and that low pressure here pulls the sail forward. Meanwhile, you also have high pressure from the wind blowing, and that pushes the sail forward. And the two of those provide a force in the sail. Unfortunately, most of that force is not in the direction you actually want, but it at least is a force. Meanwhile, we have the ability to steer the thing. And then we also have these other items, and I've highlighted those because those are going to turn out to be pretty key. Keel is what keeps you from sliding sideways. And then the hull and the keel also have the problem for anybody who's ever had a boat that's been sitting in the water too long and you got barnacles on it. You'll also know that there's a lot of drag, and it's really nice to not have all that drag down there. And so having that as slick as possible is something a lot of owners try to do. Well, this is ultimately a physics talk, so we can't do a physics talk with forces and not do a free body diagram. So if we take those forces and we put them together onto a single point, this is what we end up with. And so again, the wind is coming in from the left and blowing that way. And you have the various forces that we had before all put together here. And there is a net resultant vector that comes out of that. And so as we know from the sum of the forces, the net force is equal to the mass times the acceleration. And if you don't have a net force, nothing happens. Now, if you look closely, you'll see that my net force there is not pointing the way I want to go. My net force is a little bit tipped. And that's a problem. And that's just something that happens with sailboats. And that means that the sailboat's going to slide a little bit. A lot of people call that crabbing as the sailboat moves sideways. Well, it has to. If it doesn't move sideways, you won't have any water flow against the keel. If there's no water flow against the keel, then you won't have a keel response pushing to help direct or to help counter the forces on the sail. So a sailboat pretty much cannot possibly sail straight forward. Catamarans can get kind of close to that, but not quite. So all sailboats have to slide a little bit, otherwise there wouldn't be any keel response. Just like in order to have kinetic friction, you have to have motion, same sort of thing going on here. So let's go ahead and continue on this a little bit and look at it from a different angle here. So one of the questions that a lot of people ask when I'm teaching sailing is, how come the boat doesn't go over? The reality is that any pleasure craft, racing boats are a different game, but any pleasure craft is designed such that it really cannot flip over. The question that I'll sometimes get of how much wind can the sailboat handle? And the general answer is actually more than the owner can. The real problem with too much wind on the sailboat is the amount of extra load you put on all the rigging and possibly just damaging the sailboat, but you're not going to flip it over. Sailboats do flip. Any boat can flip. But what will usually happen is you get something like this where the sailboat's keeled way over and it's got a strong heel, as it's called. So the tip on a sailboat, you call that a heel, heeling. And so if you got a wave that also hit this, so the combination of a wave and the wind can flip a normal sailboat. Racing boats can flip with just the wind because they're on edge to begin with in order to get the most speed that you can, but a normal sailboat doesn't. So there's a variety of things to look at here. So notice that as the boat tips and more gets this position, you're also spilling wind. So all the wind that was hitting up here, when you're like this, that wind is now going over and you're spilling the wind out of it. And if you look at the force vector I've got here and the force vector I've got up there, you'll notice I dropped that force vector. And so as the boat tips over, the force it's making it tip drops. And so that makes it less likely to continue to go over. So that's one reason it doesn't do it. Another reason it doesn't go over is this balance point issue. So you got the center of gravity located right in here, and this center of gravity, I'm going to draw a line through it that I'm going to label as G for gravity. And then there is the righting torque. And so the boat wants to rotate around that center of gravity there. And you've got a couple of torques going on. One of those torques is buoyancy. That wants to take the boat and tip it that way. Another torque is the keel response. The keel's got a lot of weight to it. And the weight of the keel is going to want to pull the boat back this way as well. And so what happens is this spacing here between G and my vertical net forces, are really a torque around the center, which since it goes vertical, we call that the Z line. And so for people who know a bunch about boats, you'll know about the GZ, or if you're British, the GZ curve, which is basically a measure of how tippy your boat is. And if you're going to get a race boat, you'll find out that the GZ curve is pretty tight. And if you have a pleasure craft, the GZ curve is pretty generous. And so we don't generally want to be spilling the our fine wine off of the table any more than necessary. So you really don't want the boat to tip too much there. Unfortunately, we do have a thing that's going the wrong way, and that is the thing that keeps us from sliding. The keel is also not helping us when it comes to righting the boat. But fortunately, that's a fairly small force at that point. And just like with the sail, as the boat tips, that force vector right there on the keel will get less and less as we go. That's what keeps the boat from going over. Now, what about propelling the boat, that force on the wings? Well, let me step out of the way here a little bit so that I can see this one graphic. This is a spinnaker. It's a large sail you use in light wind conditions when you're running downwind in order to make your boat go faster. Spinnaker works entirely on drag. It's just a big parachute is all that thing is. And they can be fairly frightening to work with because some of these things are huge, but it's just a big parachute. And so when you're in that part of the sailing range there where the wind is blowing behind you, what's happening is when the wind's behind you, it blows right back. And so this is just like a parachute works or an umbrella on a windy day when you don't want it catching the wind, and it is. And so that's what happens when you run downwind. This diagram here, by the way, is called the points of sail. And those would be the various directions that sailors would refer to the direction that her ship is going while she's at the helm and directing the ship someplace. We're not going to worry about those various values. Most of our discussion today, though, is going to be for being on a beam reach there. And the reason for that is that's when you go the fastest, is when you're on a beam reach. When you have the wind blowing across the sails, then you can get that aerodynamic lift that we talked about earlier, where we had the wind going across the back of the sail. And in that situation, our boat is acting a bit like an airplane, and we get aerodynamic lift. Okay, oh, that was scary. So we get aerodynamic lift there when the plane is got the air going over the top, and you get the same sort of phenomena going on with the sail. So in this beam reach area, you're getting both the drag with the wind pushing on the back of the sail, and you're getting aerodynamic lift at the same time, and that will allow you to get the maximum amount of force, which is why that's where your boat can go fastest. So let's take a look at a chart for that. So this particular chart is for a catamaran, and we're going to talk about catamarans in a few minutes. The interesting thing to notice, there's a couple of things to notice in this chart. First of all, the wind speed that you can see in that box up at the top is 10 miles an hour. And yet the curve here maxes out at 15 miles an hour. This is for a catamaran again, that's fairly key. Other boats will have the same thing, but this curve will be tighter in. So what is this graph? This is a pretty complicated graph. So these curves here are speed of the craft. So that would be the 5 mile per hour curve. This is going at 10 miles an hour. And then this curve that we don't quite reach is at 15 miles an hour. The lines here are the direction of the wind to the bow or the front of your boat. And so if your boat is pointing right into the wind, so you've got these very short, very small angles up here. If you're pointing into the wind, well, party's over, you just can't go. That's all there is to it. So you can't go into the wind. You got to have the wind at least a little bit at the side. So here you can see this line, it goes up to 30 degrees. At 30 degrees, you can start to make some sort of motion. So with a 10 mile an hour wind, this 20-foot Hobie cat is moving along at about 5 miles an hour. So you're only getting half the speed of the wind. You got to get all the way over to about 50 degrees. So you're at a pretty steep angle to the wind. For a monohull boat, a regular boat that's got just a single hull, kind of sailboats that most of you picture in your head when you think sailboats, that sort of a sailboat, you can start to get your best speeds occurring right around about 45 degrees off from the wind. Those boats will go a little bit better than a catamaran into the wind, but that doesn't matter right now. At that point, your wind speed and your boat speed can be about the same. And then in the case of a catamaran especially, you can actually exceed the speed of the wind. It's pretty weird. So your boat will actually go faster than the motor that's driving it, so to speak, than the driving force involved here. It's pretty strange. Let's see if we can figure that out some. All right, so what's the wind doing? This weird sort of a thing. I want to back up one more. So everybody, I was asked to get a piece of paper out. So I want you to do something. So we're all going to do an experiment here. So I want you to hold your piece of paper and just take and blow on it. We're going to blow up near the top. Not a whole lot happens. Now I take and blow across the edge here. And if you all try that, depending upon your altitude above sea level, and I suppose your aerobic conditioning, if you do it enough, you'll get lightheaded and you can have some fun in that respect, if nothing else. You will notice that blowing over it will often lift it more than blowing behind it. So blowing over top is more effective and has greater amount of force. Anybody that's ever gone skydiving knows that a square parachute, which uses lift, is substantially smaller and lands you more softly than a round parachute that uses just drag, because the lift forces are stronger than the drag forces. So just having a big parachute is not as effective as having a wing. And that is pretty important here. All righty, so of the wind and the effect of the rain, of the lift. All right, so now let's talk about the wind now that we did that little example. So if the wind is coming from the side and going like that, that's going to be a beam reach, as we would call it in sailing. And so the wind is coming in from the side. anybody who's ever been in your car, and I'm hoping all of you who have been in your car have rolled the window down at some time and put your hand outside the window and tried to surf the air a little bit with your hands at some point in time. If you didn't, you probably don't belong in this talk. Anyway, inquisitive people do that, right? And so when your car moves, you get the wind that blows by because of the motion of the car. Same thing happens on a boat. And if you've ever been on a power boat, for example, and you're ripping along with a skier behind you, you've got all that wind blowing in your face that is because of the motion of the boat. And so that gives you this velocity of the air, which is an apparent velocity because of your motion, and you have the velocity of the wind from the wind itself. Well, the actual wind your boat senses is the combination of that. And so we do a vector addition. And so the apparent wind is coming across your sail in the direction that I've got shown there, and you're getting a dramatic amount of lift. So you get a pretty strong lift force there. And notice that that vector is actually larger than the wind itself. And so your own motion gives you more wind, which gives you more lift, which helps you get more motion. It's like a perpetual motion machine of some sort, but not quite. That's pretty weird, but you're actually able to get some substantial force on the sail that's a combination of your motion plus the actual wind. All right, so one of the few equations we're going to do here. So on Sherry's and my little 18.5-foot sailboat, now our mainsail is 8.3 square meters. And if you just take regular air density there and we run, in this case, I'm going to run downwind. So we're not going to have any lift issues. It's going to be not one of your best arrangements, but it just is an easy one to calculate. So when we do this, if we have a 10-knot wind, now 10 knots is a nautical mile per hour. And that's a whole nother talk on celestial navigation as to why we use nautical miles versus regular miles. So we'll just leave it at that. But just basically add essentially 10% to any value in knots. Just add 10% and you'll be pretty close to the value in miles per hour. So if we have a 10-knot wind, and then we put it into the drag equation to figure out how much drag force we have, we can calculate that out. We find out that we've got a whopping 40 pounds on our sail in a 10-knot wind going downwind on this modest-sized 18.5-foot sailboat. Something I want to direct your attention to here, notice that the coefficient of drag is bigger than 1. Isn't that weird? Think about that. How could that be bigger than 1? It's a drag coefficient. So here's what's happening. So as the wind blows and hits the sail, it will swirl around behind the sail. So when you got your sail here, the wind hits it, and the wind that spills over creates a vacuum back here, and that vacuum drags the sail forward, and you actually get a coefficient of drag that's greater than 1 by 30%. Pretty wild there when you're going downwind. 40 pounds. 40 pounds. The boat, in boating terms, you refer to the weight of a boat not as mass or weight. You refer to it as displacement. And that's because of Archimedes' principle, right? Thank heavens for buoyancy in Archimedes. And so what you do, you know from Archimedes' principle, when you have something that weighs 556 kilograms, or I should say masses out at, you displace 556 kilograms of water. And so because boats displace water in order to get the buoyant force, we refer to the weight of a boat or the mass of a boat as displacement. So my little 18.5-foot sailboat is 556 kilograms, 1,200 pounds. By the way, 400 pounds of that is in the dagger board, the keel that I can raise and lower on my boat. And so fully a third of my boat's mass is in one big heavy board that goes up and down to keep the boat from tipping over. And that's true for most monohull sailboats. So anyway, let's go ahead and plug those numbers in. So when I plug those numbers in and figure out the acceleration, we get this head snapping, throw you back in your seat acceleration of 3/100ths of a G. Yes, there's some serious acceleration for you. To compare that to your car, if you just take your garden variety car and accelerate up the on-ramp of the interstate and bring your speed up to 70 miles an hour in about 10 seconds or so, which is pretty common. The amount of thrust that your car is doing in that situation is 9 kilonewtons. 9 kilonewtons would be about 2,000 pounds. So 2,000 pounds of thrust in traction force from your tires to accelerate your car compared to 40. Okay, and so that's why this is not all that impressive. But is it real? Did we do the calculation right? What does that mean? Okay, so for our little bitty boat with both sails going, it turns out that that calculates to an acceleration that brings me up to the hull speed of the boat, we'll talk about that in a minute, to 6.3 knots in about 5 seconds. And that's not true. When I do this with my boat, when I've got a 10 knot wind on the boat and I turn it around and I face downwind, it doesn't get to speed in 5 seconds. It's more like 10 or 12 seconds to get up to speed. And so this sad acceleration is minuscule compared to the real acceleration is minuscule compared to that. So this is 5 seconds. It really takes more like 10 or 12. And so that means that our actual acceleration is more on the line of 100th of a G. Guess what? Sailboats don't generally have seat belts. That's partly because we don't generally collide with things either, but that's another issue. All of this assumes no water. So here's the problem. That's the force in the boat if it just slides, and it might be okay if it was an ice boat. But for a sailboat, you've got water in the way. You've got 2 big waves you have to push here. One of those waves is the front of the boat, the bow, and the other one is the wave that comes in at the back. And if you look at boats carefully, you'll see 2 sets of waves coming off of them. So you're pushing a wave in the back that comes around from swirling behind it. That's why you'll see a lot of sailboats, especially, will have a tapered tail end to them. That's to reduce that stern wave, so you only have the bow wave. So you got this stupid water in the way here. Okay, who put that there? So you've got a couple of choices here. You can push the water out of the way. You can just simply cut through the water and ignore the wave, or you can just simply get out of the water. Well, the waves aren't the only problem. You also have the fact that your hull drags. It's got resistance. There's friction between the water and your boat. So there's a variety of things you can do to get rid of the hull drag. You can polish the living daylights out of it and make it really smooth. You can carefully shape it to try and really, really carefully to make sure that you don't have any places where the water doesn't streamline by, and do careful hydrodynamic simulations and really get that right. And racing boats do that. So you can make it hydrodynamic, so it's just like aerodynamic. It would go through the fluid very smoothly. And you can polish the living daylights out of it. And if you look at people who have boats that they are really proud to make go fast, you'll see that they'll take their boats out of the water and literally wax the bottom of the boat to try and make it as slick as possible. We're not going to worry too much about that. We're going to take a look at these other options up here. All right, so let's do some calculations and figure out what's going on here. So let's figure out what we're up against. So we've got this bow wave. So I just found this random photograph on the internet, and I was just simply looking for a decent picture with a bow wave. And if you look at the link up there, you can see that the picture's name is even bow wave. Sweet. I wanted to measure how big that wave is. So I needed a scale. So I have a scale right there. Your average Caucasian male. And so I took the height of your average Caucasian male, turns out to be 1.8 meters. I used that to scale the photograph to figure out the rough height of the wave here. And then I figured out the length of the wave. What I don't have is the size of the wave this way. And just from being on many, many boats over the years, that wave, a good rough estimate is probably a meter. So just picking a meter pushing out. And then notice that over here, the wave kind of thins out. There's not a lot to it, but it's really quite high at the boat there. So that gives me an approximate volume of the wave on this one side of the boat as being about 4.5 cubic meters. And of course, it's not just one side of the boat, right? So you got the wave on this side of the boat, and you got the wave on the other side of the boat, and you got to push both of those out of the way. It's not like only one of them matters. And so you've got a total there of 9 cubic meters, and water, it turns out, is wicked heavy. Just ask anybody who's ever tried to lift a good-sized aquarium full of fish and water. You'll discover that lifting that thing up is pretty darn hard to do. That turns out to be 9 metric tons of water being pushed out of the way. Now, all right, this is a bigger boat than mine. And so the size of this boat is such that when you really figure out the boat and look at the sails they've got, I calculated out in a 10-knot wind that this boat has about 500 pounds of thrust. And actually, because of the wave and a few other things, they have probably more like about a 20-knot wind. And so using 20 knots, I calculated out that they've got about 500 pounds of thrust. But still 500 pounds, that's half a short ton. A metric ton is the same thing as a long ton, so it's about 10% more. And so this is half a ton of thrust, and you're shoving 9 tons of material out of the way. That's not good. Well, the other thing that happens is as the boat hits the wave, it's not like it's just going in. At some point, it's rising up on the wave too. And so this fairly heavy boat has to be lifted up in the air too. So you got, not only are you shoving 9 tons of water out of the way, but you're also lifting the boat up as well. Well, even in the best of times, is not a great arrangement there, right? So what are we going to do? So here is our free body diagram, what we had before. But now we're going to modify this. We're going to let the water come in here as well. So when we put the water in, we end up with the force of the bow wave, and our net force goes to 0. That's not very helpful. When your net force goes to zero, anybody who's been through even a high school physics course knows that F equals ma. If F is 0, A is 0, and you don't accelerate anymore. If you don't accelerate, your speed doesn't change and you hit a top speed. The result of that is that all monohull boats that stay in the water in the normal way are limited by the speed of that wave, because they cannot push that wave out of the way any faster than it wants to go. And so the size of that, the length of that wave will determine a little bit its wave speed. And so there's this modestly complicated formula about the length of the boat, the size of the wave, and how fast the boat goes. And basically it means not very fast. So the top speed for my boat is 6.3 knots. And if you push this thing harder, put more sails up, stuff like that, all you're doing is putting more forces on the boat, and you're not going to do anything. You're just going to damage the boat because it's not going to go any faster. The only way to get any faster is to do something else. So we need to get rid of those things. We got to get rid of the bow wave, and we got to get rid of the hull drag. That's our problem. All right, so one thing you can do is get rid of the water. And so we can just totally X the water out of this thing here. And if we do that, we get this device right here. So this is the Greenbird, and the Greenbird is a land yacht. This thing with wind at with a wind speed of 30 miles per hour, this land yacht, so to speak, got up to a speed of 126 miles per hour. That's pretty amazing. So routinely, this thing goes along at 3 to 5 times the speed of the wind. Now the wind is coming in exactly to the side. So here's the Greenbird, and the wind comes in like this. To get its top speed, it has to be a wind that is what we would call a beam reach. And then you get the apparent wind. Well, this is going so fast, the apparent wind is at 3 degrees, almost straight ahead. You're almost going into the wind. Let me change my screen here real quick and share something. So let me go ahead and show you this. So here is this thing. This is the guy sitting inside, and we're going to stop it a couple times. And so this is ripping across the dry lake bed here, and they're using a wing for a sail because that's basically what the sail is doing at this point here. And I want to freeze frame it when we get to this one spot where we can see the wind telltale on the front of the vessel. And that's not coming up, so I'm just going to call it good. I think I missed it there, so sorry about that. But this thing is going almost straight into the wind as it's ripping across the shore. So let me go ahead and change back here. Make a couple of. So anyway, this thing is going almost straight into the wind. Pretty amazing. Now, what about boats? So we're in the water. I mean, it's the whole point to a boat, right? So one thing you can do is you can just simply cut through the wave. That's what catamarans do. So catamarans will solve the problem by just simply slicing through the bow wave, and it's not a problem anymore. There are a variety of issues with catamarans. One of them is that you're essentially buying two boats. And so the bigger the catamaran, you're buying essentially two big boats because you're going to buy both hulls, you're buying a rudder, you're buying motors for both of them. Other problems with catamarans, if you're going to go cruising in it or something and you want to spend some time below decks, or if you want to have a bathroom on board, what we would call a head, it's kind of tight inside there. There's not a whole lot of room for a galley, not a whole lot of room to kick back and have a bed or something like that in there. And so you don't usually find long distance cruising catamarans that are smaller than about 40 feet, because if you get much smaller than 40 feet, you can't make this narrow enough to cut through the wave and still have room to get inside the hull. So that becomes a bit of an issue there. And so that's a downside to catamarans. But catamarans are a lot of fun, and they'll go really, really fast because they cut through the wave. Well, that's cutting through the wave. Our other option is to get above the water, get on top of the water itself. And we can do that with this device. So this is the Vestas Sail Rocket 2, and it has the world's record speed. It's got these little pods here that skim across the water, and almost the entire boat comes up on that foil, number 1 in the picture there on this thing. So let's go ahead and play this. I'm just going to leave it in this mode here. As this thing goes along, in a moment, you'll see a side view here. Look at the pod there. The pod is skipping out of the water, and then that was the foil. You'll see that almost the entire boat is on the foil, and because they have the wing sail tipped, that causes lift as well to get the other pod out of the water. So as you look here, the front pod is skipping across the water, and the back pod's out of the water, and that little sliver of a foil right there is acting as a wing. That's not even hardly touching the water back there. And so this boat holds the world's speed record for ripping across the water. And this thing went at 78 miles per hour in a 25 mile per hour wind. And so it's pretty dramatic there. All right, let's go ahead and kill that. So that's pretty awesome. We want to take and look at something else. We want to take a look at a different race. This is the America's Cup. So the America's Cup started out with boats like that. In 1851 is when it started. So the America's Cup is the most famous race, and Americans were the winners for 130 years or something. And then somebody decided, hey, the rules don't say we can't use a catamaran. And so they entered a catamaran and they won. So everybody then started saying, oh, wait a minute. And so then people started modifying their catamaran. So this is a catamaran that was flown really by Oracle in 2013. Let's take a closer look at that. It's got a foil there where they can make go up and down so they can adjust it. For scale, you can see me in the picture there. So this thing is huge. How big is this thing? Well, the mast alone is 223 feet tall. For those of you who are familiar with the Weber State campus, that's 2.25 times the height of the Stewart Clock Tower here on campus. So this is a really, really big boat. There's a close-up of that foil, and you can make that foil go up and down so that when the side that is in the water, that foil is like this, and it gives you lift and lifts the whole boat out of the water. Here's what that looks like. So here is that boat sailing. The boat's out of the water. This is a person right here. So this is somebody, there's a person right there. There's a person sitting here, and there's a couple people there on this boat. This whole boat is out of the water, and it's flying almost exclusively. There is some weight, that's in the water there, but it's only half as much in the water as it is if it's just sitting. Most of it's coming out of the water on that wing, that foil that's acting as an airplane wing underwater there. It's pretty cool. All righty. So I want to kind of wrap things up here. This is the America's Cup 2021. And had COVID not hit, Sherry and I were going to fly down to New Zealand to watch this race and join up with some close friends of ours, Fran and Jeff, and watch the America's Cup. And then we were going to tour New Zealand. So we were going to go to New Zealand in part to tour it, in part to watch this thing. These boats weigh as much as 4 Ford F-150 pickup trucks. There's a lot of boat there. It's a 75-foot long boat. And the entire boat gets out of the water on this rear foil and on this foil, and these side foils can lift up and down. And so you can see on the other side there, that foil's lifted up, and they use that for balance. Here's kind of how that works. So as the boat is sailing along, notice that the water line here is below the boat. The boat's in the air. And you have lift here, and you have lift also from this back one. And then the wind wants to push the boat over, but you have a righting moment that brings it back because of the weight of the foil that you've swung out to maximize the leverage. And you've got the boat wave all wanting to rotate around this axis right there. So that is how those boats go. And so I want to this is our last slide, and we've got just a few minutes left. You can see the boat coming into view here, and that's going to be your foil. That's going to be the side foil, and you're going to get some lift from that. So now we're going to do an animation here where they're going to be talking about it. This is unimportant. We don't have to worry about those words, but you can see that they can put them down when they want to dock it. So there's plenty of room to get it into the dock. And then when you're out sailing and you've got the wind coming from the side, you can put the one out of the air. And this is just telling you what I'm telling you. Don't have to worry about those. And so they can move those in and out to make the boat stable, depending upon how much wind there is as the boat goes. And that's as far as I want to go on that one. Let me kill that screen. Let's pop over to this one. And so now we're going to see this animation as this boat comes into use. So this is a pretty awesome animation. Notice the boat is out of the water. There's only 2 pieces of the boat touching the water. You've got the boat, on those on the sail there, and on the foils lifting it out. So here's the two of them racing, and you can see that they're changing that foil, lifting it in and out of the water there. So that's how those things would sail. So that looks great. And they've got this dramatic animation. This is actually a pretty good animation. That looks pretty realistic as those guys are working on those winches. So let's go ahead and kill that. I want to take a look at reality. So it's all good and well to have a drawing, right? Anybody can do a drawing. Let's see what the real boat looks like. So here's the real boat. So we're going to watch this thing, and this is in a trial run. Here it goes. This is a boat that weighs as much as 4 F-150 pickup trucks. Now they're struggling a little bit as they're trying to adjust it. Notice the bow is occasionally tipping into the water. They're pretty intent on not flipping this thing over. So they're being a little bit tentative about adjusting the thing. And you got this power boat here that's got 4 big honking motors on it. And I'm running along after this thing. And so it's turning around here. It's going to hit me. Oh, no. Okay. Phew, boy, that was close. And you can watch the wing go up, the foil go up and down here as they transfer to that one being in the water. And this one's going to come out of the water as they make the turn here. And they're feeling comfortable with it. So, yeah, they're trying to bring it up. And you notice the bow tipped in there a little bit. So there's definitely a learning curve as they try to figure out how to fly a sailboat. This isn't new, by the way. We've been doing hydrofoils for a long time. Here's a sailboat from 1953. All right. Anybody have any questions? You can go ahead and open up a chat if you want, or I would propose that you just simply go ahead and unmute. Now, this is a student seminar, so I'd like to get questions from the students first, if possible here.
So are these designed?
Sorry, go ahead.
When they flip, they're easy to flip back over. So is that like
Yes. And if you watch some of those animations, where I cut it off, if you go a little bit past that, there's a description where they've made this thing so it can be self-righting. There's enough torque. The main issue is getting the pressure of the water off the sails so that the sails don't act as a big giant drag to keep you from popping upright. But yeah, they will self-right.
Excellent.
So if somebody else was trying to jump in there.
Well, I think it makes sense with the last boat that you just showed us, but the one before where you had a picture of you standing next to it,
Mm-hmm.
Does it have something that you could move quickly in case there was like a large gust of wind that came in?
No, you're just screwed.
So you're just going to like
Go over. Yeah.
Okay. Does that I mean,
Oh yeah, that's
if
pretty
that happens
spectacular
during
too.
just
And they don't always go over this way. Sometimes it'll go over this way, which is called pitch poling. And there's a very dramatic photo of this enormous boat pitch poling in the San Francisco Bay Area. And that's where I took that photograph. That photograph is just south of San Francisco. So that's at the Oracle headquarters, just north of San Jose. There, but yeah, no, they flip over, and it's a bugger to get them upright. You put cables on the up on here, and then you attach that cable to something that can pull it out, and then that'll right the boat and pull it back upright. But yeah, no, that's a bad thing.
So it looks like this technology is used a lot for competitive sports. I'm wondering what kind of applications this might have for commercial sort of uses.
So there are commercial vessels that have a combination of things. Particularly, it would be like marine ferries, where somebody wants to get their cars and passengers across some large area really quickly. So they have built marine ferries that use hydrofoils to get the ferry up and out of the water. The main problem is it's expensive because you have to put in a lot of boat motor power because marine ferries don't want to use a sail because people don't want to depend on the wind. They want to be able to get from one part of the Gulf of Alaska to another part of the Gulf of Alaska or across the English Channel every time, whether the wind's blowing or not. And so those use power. And in order to be able to do that, it takes a lot of fuel to get the boat going fast enough to cause it to rise out of the water. And so some of the ferries are actually designed as a combination. The idea is to lift the boat a little bit out of the water to help reduce the drag, but not necessarily all the way out of the water. So they do use it for that. And there is a personal sailboat that normal people, slightly more well-heeled normal people, can buy, and it's about 10 or like 15 to 20 feet long. I forget the size. It's called the Moth. The Moth is a small sailboat that has these hydrofoils underneath it, and it's a 1-2 person boat, and you can sail it just exactly this way. And these things are not cheap, though. They're pretty expensive. The other thing where some of you may have seen it is you can occasionally see somebody going behind a boat like a water skier, but they're sitting on a chair, and the chair is rising up out of the water. Well, the chair is rising out of the water because it's sitting on a blade, and the blade goes down to a wing, a hydrofoil, under the water, and then you go pulling behind your boat like a water skier, but you're on a chair.
Yeah, I have a question. So on one of the next slides, when you showed the animation of like the newest boat, they showed two of them racing each other, and they came really, in that animation, they came really close to each other. Do they actually, like in real life, do you have that kind of fine control where you can actually get that close to each
I
other?
hope so. They do occasionally hit. It's not, you get penalized for that, but they try not to hit each other for a whole bunch of reasons, not the least of which is these are expensive boats. This is not your poor mean sport. So yeah, they do occasionally hit, and there's more than two racing. There's a bunch of entrants that race in these things.
And are the foils capable of taking a hit like that? Because that, I would imagine that the foils would hit. Are they capable of withstanding that?
Hope so. They'll find out. So the reality is that these have to be wicked strong. And that's why this small sailboat, the Moth, in fact, one of the listeners here in our audience, Erdan, very much wants to buy a Moth, and he's the one that introduced me to it. So when he was talking about that, I thought, ooh, I want one of those. And I looked at the price and I thought, oh my gosh. And even a used Moth is $10,000. But the reason that these little boats are so expensive is that making this thing strong enough is not a trivial engineering feat. And so you have quite a bit of engineering design in there. The other thing that makes it expensive is these are generally not production boats, so they're not making hundreds of them, and that makes it expensive as well. Did I answer your question?
Yeah.
Okay. Any other questions?
Yeah, I got a quick question.
Sure.
So I've noticed these racing boats and the boats made to set these records tend to be much larger than the other boats. Is that just to accommodate a larger sail, or is there any other reason behind that?
Well, there's multiple things. First of all, when the America's Cup started, it was back in a time when we were racing from New York to San Francisco as part of a large global trade thing. We were also making runs with sailboats across to China and stuff like that. And so, in fact, one of the world's records for taking a large sailboat from New York to San Francisco around Cape Horn is still held. Nobody's beat it, and that's held for over 100 years. Nobody's beat it in a comparable boat. Catamarans have beat it, but that's not fair. And so the longer the boat is, the faster the wave by a small amount. And so a longer boat means that you're going to go faster. So that's one issue. And then the other issue is these old boats from the maritime trade in the 1850s were the boats that were being used to make these races. And that's where the origins of the America's Cup comes from. And the result of that is that the boats that are in these races were that size. And if you make the boat any smaller, it can't push the wave any faster. And so that made all these boats that size. And then when we started going to boats that were out of the water or catamarans, they just maintained that size class. And so now it's a very tightly defined thing. The boats are they must be, in this case, 75 feet long, et cetera. So it's kind of a long, complicated answer to your question, but it started out with big, long schooners at the time, and that's where they get the speed from the length in part.
Gotcha, thanks.
Erdan added a comment. He says that at least on the Moth, those foils are actually very fragile, which makes sense because it's not all that big of a boat. These large boats here for the America's Cup, they're still not something they want to hit. But on the other hand, they've got to be strong enough to be able to lift this entire boat in the air. And so those are pretty burly. Anybody else?
I have
Yeah,
a question.
Go ahead. You can go ahead.
Okay, sorry. Back on the slide where you had your speed at the different angles for the catamaran.
Yep.
Yeah, that one. So you have that shape and you said that's for a catamaran. Is that pattern similar for the different types of boats, or how does that vary?
Yes. Yeah, so it'll be the same basic shape, but what'll happen is it will come in to where it's closer to the wind speed. It's hard for monohulls to get much faster than the wind speed. And so this lobe will come in quite a bit. And the other thing that'll happen, and so for example, my boat at 6.3 knots, here's 10 miles per hour, 6.3 knots, it could be around 7 miles an hour. My boat simply cannot go faster than that. So this lobe would come into about there because that's limited by the hull speed of my boat. The other thing that'll change is this will come down a little bit more on some boats and then come in a little bit more. And then where this comes in here on a catamaran, it comes in a little tighter. On Sherry's in my boat, it's a little bit more up here because a monohull can go into the wind a little bit better than a catamaran can. And that's because the keel does a better job and a few other issues. But it's the same basic shape, Sarah.
Okay, thank you.
Harrison, I think you had a question.
Yeah, so you talked a little bit about how the sailboat is prevented from keeling over by, no surprise, the keel. And then you said that there's another direction in which the boat can tip, and that's in the, let's say, the long ways direction. I don't know the right term for it. So
Pitch
let's
pole.
imagine, sorry, what was that?
Pitch pole.
Okay, that makes sense. Pitch pole. So one example of that, I imagine, would be if you're running downwind. Now, I imagine what prevents it from tipping in that direction is if you're running downwind, the front of the boat is going to enter the water more, meaning there's more buoyancy towards the front of the boat, which counteracts that torque on the mass. Would that be correct to say?
So what happens on a normal boat, a monohull, you've got all of this mass of the boat and you got the sail here, and you just can't lift that much boat up. It's really, really so true with these guys. So on these guys here, there's just not a lot of mass involved. And you also have this very, very knife edge like front end here that's cutting through the water really well. And so in that situation, tipping it over this way is a much easier thing to do. And so you'll find that personal experience here, that you can pitch pole a catamaran. It is a, let's just say, fairly dramatic event when it occurs, and you do go airborne. You don't stay with the boat when that happens. If you've ever seen a trebuchet, you'll kind of get the sense of what it's like to be thrown by a trebuchet. Is what it is like to be pitch poled, and it's not great. But what's happening there is these dig in. You see that that's not too high above the water. And as soon as that digs in, well, then it's party over. The whole thing just flips.
Yeah, so, and then I had a second question about the AC-75 towards the end that you were talking about, that boat. Does it ever run downwind? Because it seems like it'd be especially susceptible to that pitch tilt, I think you called it.
Pitch pole.
Pitch
Pitching
pole.
forward like you're with the pole, the mast. I'm not sure exactly where the name comes from, but PITCHPOLE. So you're talking about not this one, but you're talking about this one?
I was talking about the one towards the end. So if it's the AC-75, it was red. Yeah, that one.
Yeah, okay.
Yeah.
I don't know that these will pitch pole. What's going to happen, remember when the video, the nose of the boat kept touching into the water there. I think what's going to happen there is you're going to nose in. By the way, for those of you who are into sailing, notice a funny thing here. What's missing? There's no keel. This boat it's a sailboat, big sailboat, no keel at all. That's pretty wild. This forms your keel here. In any event, I don't think you could pitch pole one of these, but I don't know that for a fact. Race boats are way more on edge. And so boats like the Volvo Open Ocean Race and some of these other big races and stuff, these boats are being pushed right to their limits, and the likelihood of one of them flipping over is much higher.
All right, thanks. I do have one more question, but I won't ask it if anyone else wants to ask something.
So does anybody else want to ask anything, or are we going to call this good? Well, go ahead, Harrison.
All right, cool. Yeah, so is the keel a uniform density, or do they put more mass like on your conventional sailboat, like towards the bottom of the keel?
Yes. So it's both of those. There are a stunning number of different keel designs. Every boat designer thinks they have the greatest new idea. And there's also keels designed for different situations. If you're in the open ocean, like who cares how deep your keel goes down? You can make the keel go down really far and not have it really, really heavy, or you can make it come down just a little ways, but still be quite heavy. You can also make it much longer, make it heavier. So you can make it long, short, tall. The boat that Sherry and I are in the market for eventually now is called a Seaward 26RK. And the RK stands for retractable keel. And so that keel will go up and down on a large shaft, and it's a bulb-shaped wing that weighs about half a ton that is down on this large shaft that we can move up and down. And that way you can go into shallow water and bring the keel up, but just not use as much sail. Or you can, let all the sail go out, be in deeper water, and let the keel go down. So it's an adjustable keel, and in that case, most of the mass is concentrated in a big bulb on the bottom of it. So it varies. There's if you ever are out by the sea anywhere and you're near some marina, the marinas pretty much always have a dry storage area near them, and you can just kind of drive past and look through the chain link fence at the boats in there, and you'll see an amazing number of different fins, keels, that are underneath the various sailboats. It's pretty amazing.
Thank you.
Anybody else? All righty, well, we'll consider that good. I hope everybody had fun, and I hope that our established open ocean sailors that have way more experience than I do, I hope you got at least something out of it, if nothing else, the mass of the wave in front of your boat. And so let's hope that everybody enjoyed something or found something in there and found us to be a little bit more lightweight of a talk than we'd normally have on this stressful week. So everybody have a great day. Talk to you later. Thank you for joining us.